Let's look over the material for Chapter 9. While you'll notice there are a lot of different categories here, what I'm going to do for most of these is I'm actually just going to solve problems that are examples of them, so we'll go over those topics there. Make sure that you still remember, though, that there are important concepts related to these in terms of just, so what do I mean by the term molarity? How does that relate to moles and volume? Things like that. Know what the terms actually mean. But most of these will be covered by actually going over the questions. The only that are completely conceptual in this area would be, first off, the idea of electrolytes. That's just a way of saying, okay, how soluble is something, right? Because we learned that when we had something in water, if it was an electrolyte, that means it would break apart, and that would allow our electrons to transfer, and then we see like our light bulb light up. So we can figure out if something was an electrolyte or not based on its solubility. You should also be okay with memorizing your strong acids and strong bases. Don't forget to do that. You should recognize those. If I say nitric acid, for example, you should know it's HNO3. So make sure you know how to do that. The rest of these topics will be covered by doing examples of them, so we'll just go and get started on these. Just like the note says, I purposely don't label these questions because sometimes it's trying to figure out which thing you're actually trying to do, and one or two of them are actually Chapter 8 questions, but the idea is they'll be mixed together, so I want to practice them like that. So let's start at the beginning. You'll also notice my slides look a little different. I just made sure there was enough room for me to solve the problem. All the problems are still here, but I just removed some from certain slides and put them on other slides. That way I could actually solve them at the bottom. So our first question, we know we have 0.250 moles of HCl, and we have a 1.00 liter solution. What's the molarity is the question, so what's our concentration? Well, we know that molarity is equal to moles over liters. So we know it's going to be equal to 0.250 over 1.00. And in this case, moles over liter, we can write it as big M. This is going to give us just 0.250, right? Because 0.25, anything divided by 1 is itself. So when we get that, we simply get 0.250 molar. That is our concentration of our HCl. The main reason I'm doing examples like this is there will be a few, especially early in the exam, that will be something where you just have to do one step, where it'll be like, here's moles, here's volume, what's the molarity? Don't overthink those and think, oh my gosh, I've got to do like 12 other steps. Sometimes it really is that simple. I want to make sure you know how to do the basics. So let's try the second, where we've got it in a slightly different order. So here we know that we've got, what is the molarity if we have 3.50 moles of HCl in a 0.500 liter solution. You notice it mentions a solution of water. That just lets you know it's an aqueous solution. You don't have to do anything with the fact that it's H2O. I don't have to create a reaction or anything. So this one is actually just the same type of problem. We have 3.50 moles over 0.500 liters that it's in. And from there, we get the fact that we have, I'm pretty sure it's 7, yep, just making sure, that it would be 7.00 molar HCl. So yes, if you get a question where it's just one step, that's okay. So now let's ask one where we've got some slightly different information. So we're going to have 2 liters, 2.00 liters of a 1.50 molar in HCl solution. And the question is, how many moles do we have? Well, for this, we need to rearrange our molarity equation. Molarity equals moles over volume. So we also know that this problem we want to know the moles. So we can know that moles are equal to our big M times V. V just stands for volume. So in this case, we have I'll write the molarity first. It doesn't change it. Multiplication is communicative, but just to make sure it's consistent with the equation, 1.50. And I'm going to rewrite the molarity as moles over liters. Remember, that's what molarity stands for. That can help us make sure we know our units are right. And then here in our volume, we're going to get 2.00 liters. Our liters will cancel. And we are left with, we have 3.00 moles of NaCl. Okay, the question then asks the second part. What would happen if instead we had 3 liters of 1.25 molar? So this is just doing the same question again. Okay. My pad locked up for a second, that's why I was doing that. So, if we have our moles still equal to m times v. So we have 1.25 moles per liter times 3.00 liters. And from that, we get that we have 3.75 moles of our NaCl. Okay, so hopefully, but the three on this slide are hopefully fairly straightforward. The goal is to do a few where it's just about rearranging that initial equation, not doing something more like reacting it or anything. We'll have a few of those. Okay, so now I have another question. If you want to have 2.5 moles of potassium fluoride and you have 0.5 molar potassium fluoride solution, how many milliliters of solution do you need? So for here, we're going to go, we know we have 2.50 moles, and it is 0.500 molar. So if you remember right, for our molarity equals moles over volume, we can also rearrange that so that V equals moles over big M. So we get the volume would be 2.50 moles divided by 0.500, and it's still moles over liters. And remember, if we've got a complex fraction, right, the numerator down here is going to cancel the one up here. And when we divide by 1 over L, it reverses it just to L. So from here, we get that we would have 5.00 liters. That's how much we're going to need to get the number of moles we want. I'll leave you to do the next problem, the what if you want 3.75 moles. It's the exact same question with slightly different numbers, just like the two previous had two questions that were basically the same. So the only tricky part here is just making sure you're comfortable with units when you have fractions inside fractions. Otherwise, it's just rearranging that equation. So now let's look at something where we start with grams rather than moles. So we're going to have 25.5 grams of silver nitrate, and we're going to have it dissolved in 0.100 liters of water. And we want to know what the concentration is. So that means we want to know the molarity. So first things first, we've got to get our 25.5 grams into moles. So 25.5 grams of silver nitrate. Then you have to look up its molar mass. So silver has a molar mass of 107.86 or 87. Nitrogen has a molar mass of 14.01. And then we have 3 oxygens, and that's going to have a molar mass of 48, because remember there are 3 of them. So from there, we get that the molar mass is going to be 169.88 grams of silver nitrate for every 1 mole of silver nitrate. 25.5 divided by that will give us that we have 0.150 moles of silver nitrate. And now our problem is just like before. We've got moles and liters, we want molarity. So our molarity is going to be equal to 0.150 moles over 0.100 liters. And from there, we're going to get that we need 1.50 molar. That's what our solution is going to be if we were to add 25.5 grams dissolved in 0.1 liters. So that's our concentration of our silver nitrate. Okay, so for there, we'll try one more example like this. You'll do a bunch of these too, where you've got grams, you have to get to moles, get to molarity. So now let's try the next one. If we have 42 grams of sodium hydroxide and we want to make a 1.5 molar solution, how much water do we need to have? So we have 42.0 grams. I'm going to go ahead and turn this into moles since we know it's just like the previous step. So sodium, a molar mass is 22.99 plus 16 for the oxygen plus 1.01 for the hydrogen. It's got a molar mass of 40.00 grams per 1 mole of sodium hydroxide. And from there, we get a number that's about 1. It's 42 divided by 40. That's going to give us, we have 1.05 moles of sodium hydroxide. And so, if we go back to our equation, we know that molarity equals moles over volume. And I want to find volume, and I've got the other two. So we rearrange that to volume equals moles over molarity. And this is equal to 1.05 moles over 1.50 moles per liter. The moles cancel. We are left with 0.700 liters. That's how much water we would need to add. Also note that if the problem had asked for it in milliliters, like it did a couple questions above, you would need to convert that to milliliters, and that would be 700 milliliters if we were to have to do it that way. I believe I may have forgot to do that conversion up above when we were doing that, so just make sure you answer the problem with the question it's asking. So if it asks you for something in milliliters, make sure to give it that way. Okay, so let's go on to the next example. If we have 125 milliliters of 5 molar sulfuric acid, and I want to dilute it to 0.1 molar, what should the final volume of our solution be? How much water would we need to add to the initial 125 milliliters to get that final volume? Okay, so this is a case where it is a dilution. We don't have a reaction happening, so we could use M1 V1 equals M2 V2. And we want to know, we know the starting molarity and we know the final molarity we want, so we want to know the new volume. So that's going to be our V2. I'm going to have 1 be our initial, 2 be our final. So our final volume, V2, is going to be equal to M1 V1 over M2. So from that, we get 5.00 molar times 0.125 liters. Don't forget we're converting things into liters. And it's all going to be divided by our new concentration, which is 0.100 molar. Our molarities cancel, and we're going to be left with liters, like you would expect. So 5 times 0.125 divided by 0.1. Our new volume of our solution, we're going to have 6.25 liters to be able to get this new concentration of 0.1. You'll notice it's a fairly significant increase, and that makes sense because we're going from this very concentrated 5 molar to 0.1 molar. So we've got to add a lot of water to that. The next question was, how much water would we have to add to the additional 125 milliliters to get that final volume? So the volume to add, V add, would be equal to 6.25 liters minus 0.125 liters. Because remember, we start with the original volume. Our M1 V1 equals M2 V2 equation isn't giving us the volume to add, but the final volume to get to. So 6.25 minus 0.125 is going to give us that we're going to need to add 6.13 liters. That's how much water we're going to need to add because there's already some there. Same idea, remember also that we've got 2 decimal places in our sig figs, so that's why I go to 0.13 rather than writing out 0.125, because we don't have enough decimal places in our 6.25 number. Okay, so this is the case where we actually use M1 V1. There's a dilution. That's the time we do it. And it has to be that we're not doing some reaction with it, right? Okay, from there, we've got another one. If we have a 3.5 molar solution of lithium hydroxide, and we wanted the final solution to be 1 liter, that is 0.5 molar, how much of the 3.5 molar solution should you start with before adding water? So the question is asking us basically, okay, what's going to be our starting volume, right? Because it tells us we know where we want to get to, and we know the concentration we're starting with, but we're not sure how much water we should start with. So we have M1 V1 equals M2 V2, and we want to solve for V1. So that's going to be equal to M2 V2 over M1. So our final molarity is going to be 0.500 molar. Our final solution has to be 1 liter, we said. And we know that the starting solution has a concentration of 3.50 molar. So what should our starting volume of stuff be? So we have 0.5 times 1 is just 0.5 divided by 3.5. We're going to get that we should have 0.143 liters of our solution. Note that a lot of this is really just identifying what do we know and what are we trying to find out. That's really the only thing that'll ever be tricky in the dilution questions much. Okay, so let's do our next question. You do a titration and figure out a diluted solution you made was 0.12 molar HCl. If you started with 100 milliliters of your unknown solution and diluted it to 1 liter, what was the concentration of your starting solution? So this one again is about finding our question. You'll notice it even asks us, what was the concentration of our starting solution? So that means we want to find M1 this time. So rearrange our equation, M1 V1 equals M2 V2. We can rearrange that to M1 equals M2 V2 over V1. So Our final molarity, we figured out from the titration, was 0.120 molar. We also know the final volume was 1.00 liters because that's what we eventually got it to. And we know that we started with 0.100 liters. That's from the 100 milliliters. So we want to know what would be our starting molarity. We have 0.12 times 1 doesn't change it. Divided by 0.1 just moves the decimal. So we're going to have a 1.20 molar solution of HCl at the start. Notice again, this question is just identifying what is it asking and what information do we have. Okay, let's try doing something now where we're not just going to do dilutions. Let's do some more complicated questions. So this is going to be a titration. So we titrate an unknown concentration of HCl with 0.1 molar sodium hydroxide. The acid has a volume of 10 milliliters, and you have to add 14.6 milliliters of NaOH to neutralize the acid. What is the concentration of the HCl? So for this, we're going to need a balanced chemical equation first. We know that HCl plus sodium hydroxide, when we add an acid plus a base, we're going to get water. That's always one of our components, right? And we're also going to get a salt, in this case, NaCl. Note that the problem doesn't ask anything about solids created or anything. If it did, you would need to go through and look up your solubilities to know whether your NaCl would be soluble or not. Given, I have a feeling you've heard NaCl a lot, we know that salt will dissolve in water, so that's clearly aqueous. But the problem doesn't make us use that information in any way, so I'm not worried about it right now. So, we want to know what the concentration of our HCl was. So we can figure this out because we know that we said that it neutralized the acid, that means it got rid of all of it. So I know how much sodium hydroxide I added, so I'm going to figure out how much HCl there must have been. So our sodium hydroxide, we know that we had, let's see, we had 14.6 milliliters of it, of sodium hydroxide, and the concentration of that was 0.100 moles per liter. I'm just rewriting my molarity of sodium hydroxide. We also know that we're going to use later the volume of our HCl was equal to 10.0 milliliters. We don't have to worry about it yet, but we'll use that later. So the first question is, how many moles of sodium hydroxide did I have? The reason I asked that question is because I know I need to use a balanced chemical equation up here. And whenever I need to use that balanced chemical equation, I've got to get things towards moles so I can go from one compound to the other. So here, we're going to start with the fact that we had 14.6 milliliters of sodium hydroxide. And our first step is to get this into liters because we can't use our molarity without that. So we know that for every 1,000 milliliters of sodium hydroxide, there's going to be 1 liter of sodium hydroxide. From there, we're going to get that we want to go from liters to moles now. So we know that for every 1 liter of sodium hydroxide, there are 0.100 moles of sodium hydroxide. And that's just from using my molarity as a coefficient, as a conversion factor. So from here we get 14.6 divided by 1,000 times 0.1. We're going to get that we actually only have 0.00146 moles of sodium hydroxide. So now what I've got to figure out is how does that help me find how many moles of HCl we have? Well, we know that this is a one-to-one relationship. So 0.00146 moles of NaOH, we can then convert that to HCl because we said we completely reacted with it, so that means they have to be equal. So 1 mole of NaOH is equal to 1 mole of HCl. And from there, we will get our 0.00146 moles of sodium hydroxide, of HCl. Yeah, because we made that conversion. We converted from sodium hydroxide to hydrochloric acid. And we know that we want to know the concentration. So concentration in this case is just moles over liters. So I'm going to take my 0.00146 moles of HCl, and I'm going to divide it by 0.01000 liters. And that's just from up here. We're using that number. If you need to, you can write out the conversion for it. But if you're really comfortable with moving the decimal, I'm okay if you just write it like you did, like I did. But we know there's 1,000 milliliters in 1 liter. That's where I'm going to get the 0.01000 liters from. So when I do that problem, I divide by 0.01. I'm going to get that the HCl must have had a concentration of 0.146 molar. Where'd my answer go? There we go. 0.146 molar HCl. So that's our concentration. That's what the problem asked for. It then asked another question. What would be the concentration if the unknown acid was actually H2SO4? So the first thing I want to show you is where would that really change? What's going to happen differently? So I want to keep this stuff on the slide, so I'm going to write towards the top here. But we know up here that H2SO4 plus NaOH, we're going to make some water with it. That doesn't look much like an H. That's supposed to be an H. There we go. H2O. Plus, now we're going to get sodium to sulfate. Remember, SO4 is a 2- charge. Sodium has a +1, so I need 2 sodiums. So let's try balancing this equation. You'll notice it doesn't start off balanced like the other did. Well, we know that, let's see. I'm going to need 2 sodium hydroxides, clearly, because there's 2 sodiums on the right and 1 on the left to start with. And that's going to give me 2 oxygens. 2 extra oxygens, because we've got the 1 from the SO4, those 4 are accounted for, but we don't have 2 accounted from here. We also have some more hydrogens. We actually have 4 hydrogens on the left, but only 2 on the right. So if I make 2 waters, now there's going to be 4 hydrogens on the left and right. You can also count that the sulfurs, there's 1 of each, and there are a total of 6 oxygen atoms in both. So that ends up being our balanced chemical equation. The issue with this, you'll notice, is that H2SO4 plus sodium hydroxide do not form a 1-to-1 relationship. That means down here, when we wrote this conversion factor between HCl and NaOH, we would actually get that it would be a 1 at top and a 2 at bottom, right? Because you need 2 sodium hydroxides to counteract every H2SO4. That means you're not just going to get 0.00146 moles of sulfuric acid. So what I'm going to do now is I'm going to erase this part of the slide, but I'm going to use this information. I'm going to write it down. Because up to this point of the problem, this 0.00146 moles of sodium hydroxide, nothing changes. So let me write that down so I can rewrite it on the slide. You notice up to that point, we haven't used the fact that it was sulfuric acid. We just needed to find the moles of sodium hydroxide. And that doesn't change in this problem. So, okay. So we'll rewrite our balanced chemical equation really quickly. We have H2SO4 plus 2 sodium hydroxides. We're going to make 2 waters plus an Na2SO4, a sodium sulfate. And we know that there was, there was 0.00146 moles of sodium hydroxide. When we do that conversion, we go that for every 2 moles of NaOH, there's 1 mole of sulfuric acid. So 0.00146 divided by 2 is going to give us that number. I'm going to go with the scientific notation because there are so many decimals. 7.30 times 10 to the minus 4th moles of H2SO4. The problem said what would be the concentration of the unknown acid was actually H2SO4. Nothing was changed with the volume. So we have 7.30 times 10 to the minus 4 moles divided by the fact that we have 0.01000 liters. So divide that by 0.01. As you expect, it moves the decimal a bit. So we get that this would be 0.0730 molar H2SO4. So you notice the concentration went down when we did this. That's because the sulfuric acid is able to use up sodium hydroxide more easily. That means that it needs more sodium hydroxide to get rid of it, so that's going to mean a lower concentration to react with the same amount. Okay, so that's an example of a titration question we could have. And also, this is why you have to worry about the balanced chemical equation, because if it's not 1-to-1, you're not just going to get a number that works out easily. You'll have to actually pay attention to the equation. Okay, so we're going to look at 2 more questions. Photosynthesis makes glucose with oxygen to form carbon dioxide and water. According to this reaction, 6 CO2 plus 6 water makes 1 glucose plus 6 oxygen. You don't have to know that C6H12O6 is glucose. So if we have 4 moles of CO2 and 6 moles of water and 1 mole of oxygen, how much C6H12O6 can you make? So the first part of this question is to recognize that some of this information isn't actually used. So it wants to know how much sugar we're going to be able to make. It gives us three numbers: the moles of CO2, the moles of water, and the moles of oxygen. You will notice that the moles of oxygen is on the right. That means it's not a reactant, so it has nothing. We're not going to use it to help us make the C6H12O6. So we don't actually need to do anything with that number at all. Instead, we need to figure out which is our limiting reactant, our CO2 or our water. So for 4 moles of CO2, we're going to get that for every 6 moles of CO2, we can make 1 mole of glucose. And that's going to give us 4/6, which is equal to, we're just going to go with 0.67 moles. Note that this problem, as listed, only has 1 sig fig, so if you put 0.7, I wouldn't count off. When I write it on the test, I'll make sure there's more than 1 sig fig with it to make it more reasonable. So, the other possibility would be that it was the 6 moles of water. So we have to check that one as well. And we see that there are 6 moles of water for every 1 mole of C6H12O6, so our glucose. And for there we get that we would be able to just make 1 mole with that. Now if we compare this to, we'll notice that the number with the CO2 is lower. That means CO2 is our limiting reactant, which means that we can only make 0.67 moles. And this is because we're going to run out of CO2 before the water. So even though the water could make more of the sugar, we don't have enough CO2. So we don't actually get to the 1.0 mole mark. So this problem hopefully wouldn't be too bad. It's mostly just being able to identify excess information. Because some people I've noticed when they do a question like this would have used oxygen as their limiting reactant, even though it's not a reactant, it isn't involved in making sugar at all. It's actually a product that you get at the end. So let's look at another example now. So using the reaction, potassium sulfate plus calcium iodide makes calcium sulfate plus potassium iodide. How much calcium sulfate can you make from 24.5 grams of K2SO4 and 25.6 grams of calcium iodide? So this is just another example of a limiting reactant type question. So, except in this case, we're making a solid, so it's a precipitation reaction. That's why we have it in this section. So we'll start with our 24.5 grams of K2SO4. We know. So let's see. I got to look up all these. So potassium has a mass of 39.1. We have 2 of those. We have 1 sulfur, which has a mass of 32.07. And then we have 4 oxygen, which has a mass of 64. So this is going to have a molar mass of 174.27 grams of K2SO4 for every 1 mole of K2SO4. We also, since we're doing a limiting reactant, we want to actually make a product. I'm going to make the calcium sulfate. This problem doesn't tell you which one to make, so you can do either. Oh no, it says how much calcium sulfate can you make. So yeah, that's what I'm going to use. We're not worried about how much potassium iodide we could make. So 1 mole of K2SO4 goes to 1 mole of calcium sulfate. So we have 24.5 divided by 174.27 times 1. We get that we could make 0.141 moles of K2SO4. So now let's check with our other compound. If we have 25.6 grams of CaI2, or calcium iodide, now calcium has a mass of 40.08, and iodine has a mass of 126.90. So we'll add those together. Remember to multiply by 2 for the iodine since there's 2 of them. And we're going to get a molar mass of 293.88 grams of calcium iodide per 1 mole of calcium iodide. And again, we end up with a 1-to-1 relationship of 1 mole calcium iodide makes 1 mole of potassium or calcium sulfate. Scratch that out. So 25.6 divided by that, we get that this could only make 0.0871 moles of our calcium sulfate. You'll notice up above I accidentally wrote potassium there. That's where it was coming from. So this up here, the grams canceled, the moles canceled, and this should actually be listed as moles of calcium sulfate. Sorry about that. That's just paying attention to what our units are there. So we see that the bottom is the one we make the least of. So our limiting reactant is calcium iodide. And this is what we're going to get for how much stuff we're able to make. It's 0.0871 moles of calcium sulfate. If the problem had asked for it in grams, you could then look up the molar mass of calcium sulfate and make the conversion from moles to grams. But this problem didn't ask for that, so I left the answer in moles. It's fine to do whichever. Even if it didn't ask for a particular one and you convert it to grams, that's not wrong. You can also do that. So let's look at one final example. So from the okay, I've got a couple more. That's right. From the reaction from the last slide, potassium sulfate plus calcium iodide makes calcium sulfate plus potassium iodide. Write both the complete and net ionic equations for these reactions. So, remember, for our complete ionic, that's where we're just going to split things up that are aqueous. So our complete ionic is going to be equal to, we've got 2 potassiums, right? Because they break up by themselves. We then have SO4 2-, because that is going to be a polyatomic ion, so it doesn't break up into the separate sulfurs and oxygens. We then have a calcium 2+, and we have 2 iodines that are -1. Then we have to write the right side of the reaction. So the right side, we're going to get that we have calcium sulfate. Remember, if it's a solid, it doesn't break up, so we don't write it broken up. And then we have a K+ and an I-. What you'll notice is that the top was not yet a balanced equation as written there, so we've got to worry about that, right? So I'm going to need, if I go up here, I'm going to need 2 potassiums and 2 iodines. So I'm going to actually need a 2 in front of my Ki. So therefore, I get a 2 in there and a 2 with my iodine. So that'll make our equation balanced, though, right? Because we have 2 potassiums and 2 iodines on the left, 2 potassiums and 2 iodines on the right, an SO2 4- and a Ca2+ on the left. And then we have a calcium, a sulfur, and 4 oxygens. So they match up even though they aren't always broken up or not. The atoms end up working out. So our complete ionic is what we have written here. There's our complete ionic. I didn't mean to cover up that minus on the iodine. So now we've got to write our net ionic. Remember, net ionic is where we're going to get rid of our spectator ions. So the potassium appears on both the left and the right, so I'm not going to write it. The 2 iodines appear on both the left and the right as well, so I'm not going to worry about those. So for the net ionic, I'm just going to write that SO4 2- aqueous plus calcium 2+ aqueous is going to form calcium sulfate. Also note that on the left side, I'm not worried about the order. That's because until they're combined, there's no special rule if I write the minuses or the plus first. But once I form things into a compound, the cation's always first and the anion's always right. That's why I've switched the order on the right side. So this is our net ionic equation. You'll notice it's smaller because all the spectator ions are gone. So now, what I'm going to look at next, let's look at one more example like this. We're going to mix some sodium phosphate and some nickel chloride. And we're going to try to figure out what the reactants would be. So for this one, we're going to have to start by figuring out whether we make anything soluble or not. That's going to be before we can write our complete ionic. So we have 3 sodium pluses and a PO4 3-. And we've got a nickel 2+ and a chlorine minus, 2 of those. So when we make the new reaction, remember we're going to reverse. We can either flip our cations or our anion, but one of them we're going to have to flip. So we're going to get NaCl, and we're going to get nickel 2+ and PO4 3-. That should be a P. I don't know why that looks like a B. Okay, so the Na and Cl just combine together, right? Because they're a plus, we're in a -1. But the nickel and the phosphate don't have the same charge. So we've got to make it so they're balanced. The lowest common multiple for the charge would be a charge of 6. So I need 3 nickels to get to +6 and 2 phosphates to get to -6. So they're going to be 3 nickels, and we're going to have 2 phosphates. So the question is this aqueous or solid? So I'm going to have to go out of this for a second, keep my work. So what I'm going to look at now is our solubility rules. I have those shown on the right, and we'll notice that if we look up either sodium or chlorine, both of those say that sodium chloride would be solid. As you expect, sodium chloride is salt, it's soluble. But on the right, we now look up PO4 3-. It's mentioned towards the bottom. And PO4 3- is mentioned it's generally insoluble with a few exceptions, but nickel is not listed as one of those exceptions. That means it's going to form a solid. So let's go back to our question now. We know that sodium chloride is going to be aqueous, and that nickel phosphate is going to be a solid. So now we can write our balanced chemical equation, and we can try to make sure we balance our atoms. So we're going to have that we have Na3PO4 aqueous plus nickel chloride goes to, we're going to form some NaCl aqueous, and we're going to form, I'll just leave that right there, the nickel 3 solid, that works as well. I'm going to put a little line here to distinguish between which lines we're working with. Okay, so it's a little far apart, but otherwise it's the same. So we'll notice right now our atoms aren't balanced, right? We don't have the right numbers of a number of the atoms. So let's try balancing them. So I'm going to start. We can pick wherever we want to start, but I'm going to try, let's see. Where do I want to start? Okay, I'm going to start by trying to balance my phosphates. So my phosphates means, we'll do the phosphorus specifically. I have 2 phosphoruses on the right, 1 on the left. So I'm going to make it so there are 2 sodium phosphates on the left. That means that we now have 2 phosphoruses and 8 oxygens, so those are currently balanced. But now the sodiums definitely aren't balanced. There's 6 sodiums on the left, but only 1 on the right. So I'm going to try to fix this by making it so that there are a total of 6 sodium chlorides. That means there are now 6 salt sodiums on the left and 6 on the right. But this now leaves me with 6 chlorines on the right and 2 chlorines on the left. So here I'm now going to write a 3. That will give me 3 nickels and 6 chlorines. You'll notice that there are 3 nickels on the left, 3 on the right, 6 chlorines on the left, 6 chlorines on the right, 6 sodiums on the left, 6 sodiums on the right, and 2 phosphoruses on the left, 2 on the right, and 8 oxygens on the left, 8 on the right. So now we're going to have a balanced chemical equation. Note that the main reason I didn't write all that out in a big long table is just so I have enough room to literally write the rest of the problem here. It's perfectly fine to go through and do that, especially for one like this. This is going to take some work to get all those balanced. This one isn't just put a 2 in front of something and you're done. So now we've got to write this now as a complete ionic. So our complete ionic, that's where we're going to break things up. So far we just have the molecular equation. So we're going to have 6 sodium pluses. We're going to have 2 phosphates, PO4 3 minuses. We're going to have 3 nickel 2 pluses. And we're going to have 6 chlorine minuses. And now we're going to make our reaction. So what does it actually turn into? Well, we will again have 6 sodiums because the sodium chloride is going to dissolve. We'll also have the 6 Cl minuses. But our nickel 2-phosphate, it's not going to dissolve, so we'll just have Ni3, and then PO4, parentheses with a 2, and that'll be solid now. So that's our complete ionic equation. Try not to accidentally cover anything up when I'm drawing my box. I'm still adjusting this thing. Okay, so the problem asks for the complete and the net ionics, so we want to make sure we actually finish the problem. So the net ionic is just where we don't draw our spectator items. So the sodiums and the chlorines exist on both sides exactly the same, so we don't need to write those. So we're just going to have that 2 PO4 3 minus aqueous plus 3 nickel 2 plus aqueous goes to nickel phosphate, nickel 2 phosphate, solid. So that is now our net ionic equation. So now we have a net and a complete ionic equation for this reaction where we only started with the 2 compounds. Okay, let's look at a few others that are just shorter versions of this. So, what solid will be created from the following reactions? If none, simply state no reaction. So you'll notice this only asks if there's a solid. That means I don't actually have to balance the equation, I just have to check whether when I combine the ions, I make something that's going to be soluble or not. So, for example, with sodium nitrate and potassium chloride, we're going to flip our anions. So we're going to end up with, we're going to have some sodium chloride and some potassium nitrate. And what I'm going to do is I'm going to write down what we're going to make first, and then we're going to go look at the table to see whether they would be soluble or not. Here, we're going to end up with some KNO3 for our potassium nitrate, and we're going to end up with some lead chloride, PbCl2. For our potassium chloride and our calcium sulfide, you'll notice for this one you have to know how to actually do the names. So we're starting with KCl, and we're going to add it to our calcium sulfide, CaS. Remember, Sulfide is just going to be the S1. If we'd had something like sulfate, that's where you have the oxygens as well. So when we react these, we're going to get K2S plus, we're going to get our calcium chloride. Note, this is not balanced. I'm not worried about that right now, but if you needed to use this reaction for absolutely anything, you would need to balance it. I only want to know what's solid. That's the only reason I don't have that balanced right there. Although this one would be easy enough to do. If you had 2 KCl's, it becomes balanced. So, then we have sodium hydroxide plus iron 3 chloride. Remember, the charge tells us the number tells us the charge on the iron. So if iron is going to be a +3, we're going to need 3 chlorines to balance it. And we're going to react it, and we're going to form, again, our sodium chloride. We're also going to form an iron hydroxide. Again, it's +3, so this is going to be 3 of those. Okay, and again, it's not yet balanced. We're not going to worry about that right now, but that is something you have to... I'll deal with it real quick. So we need 3 sodium chlorides to balance the fact that there would be 1 Cl on the right and 3 on the left. Now there's 3 on both sides. We would then need 3 sodium hydroxides because this will give us 3 NAs on both the left and right. And we now also have 3 hydroxides on the left and on the right. So now it's balanced. So now let's check which of these are going to form solids. Okay, so for the first question, we can look up our sodium chloride. Na plus has no exceptions. It's always soluble. We then look up the potassium nitrate. NO3 minus, always soluble. Therefore, this doesn't have any solid produced. We would write no reaction for the first one. Okay, while in this mode, I can't use my pen, so we're just going to have to say it out loud. So, for the second question, we form potassium nitrate. If we look up potassium, it's listed as soluble, no exceptions. We also formed lead chloride. Lead isn't listed on the left, but chloride is. Most chlorides are soluble, but Pb2+ specifically is not. So lead chloride would be a solid. So in the second one, we would form PbCl2 would be our solid. So our third question. We made potassium sulfide. Potassium's listed as always soluble, so that's easy. We know that's definitely there. We also made calcium chloride. If we look up our Cl-, Cl- is listed as generally soluble, and calcium's not an exception. So the third one would again be no reaction. You just have your ions still. We can then go to the last one. We formed sodium chloride. We've already looked that up. That's soluble. And then we formed iron hydroxide. Hydroxide is generally insoluble, and iron is not listed as an exception. So for the fourth question, the solid would be iron hydroxide. Iron 3 hydroxide. Don't forget to put that part. Okay. So our 2 solids would be here. Our PbCl2 would be a solid. That's going to be for number 2. And then our iron hydroxide would be a solid for number 4. Otherwise, the first and third would just get no reaction. That's because even though we can write the things like this, they all stay in solution, so nothing ends up changing. Okay. So, now we've got some more things to worry about solubilities. In the reaction of potassium hydroxide plus magnesium nitrate, forming potassium nitrate and magnesium hydroxide, are any of the products insoluble? So this is just another solubility question with some extra words to it. So let's go back and check. So, potassium nitrate, potassium's always soluble, so nitrates, that means it's going to be soluble. Magnesium hydroxide, though. Hydroxides are listed as insoluble generally, and there's no exception written to that for magnesium, so our magnesium hydroxide is going to be insoluble. So, insoluble. MgOH2 should get a solid next to it, because it is going to form a solid. Okay. So now let's ask a question where instead of doing this, where we're just doing what's soluble and not, let's do something where we now use the molarity to help us figure this out. So, if you had 15 milliliters of 2.5 molar sodium chloride and 25 milliliters of 1.5 molar silver nitrate together and dilute the solution to a total volume of 1.5 liters, what would be the mass of the solid at the end of this reaction? So the first thing we've always got to do with these, we've actually got to write out the reaction, right? So we've got sodium chloride plus AgNO3. If we look these up, NaCl is going to be aqueous. We've looked that one up a lot. And silver nitrate, all nitrates are soluble. So it's going to be aqueous. And we're going to make, so let's switch our ions around. We're going to make sodium nitrate. And sodium nitrate is going to be aqueous as well because all our sodium-containing compounds are. And then we're going to form AgCl. And if we look up our chlorine, this is one of our exceptions. Silver chloride is going to be solid. I'll just make sure. Yep, Cl- when it's paired with silver is insoluble. That's an exception to the rule that most chlorides are actually soluble. So that's going to make a solid. So the question asks us, what's going to be the mass of the solid at the end of the reaction? So for this one, we're going to need to know how many moles we have of both the salt and of the silver nitrate. That way we can figure out which is going to be our limiting reactant. So we need to find the moles of each as our first step. So if I have 15.0 milliliters of NaCl, I can go convert that 1,000 milliliters in 1 liter. We also know that for every 1 liter of NaCl, there's going to be 2.50 moles of NaCl. From there, we have 15 divided by 1,000 times 2.5. We're going to get that we have 0.0375 moles of NaCl. We have to do the same now with our silver nitrate solution. So we have 25.0 milliliters of it, silver nitrate. So for that, we've got 1 liter is 1,000 milliliters. And we have that it's a 1.5 molar solution, so it's 1.50 moles of silver nitrate per 1 liter of it. So when we get that, we get 25 divided by 1,000 times 1.5. So this one is also going to be 0.0375 moles of silver nitrate. So now what we need to do is we need to convert them both to our solid, our silver chloride, to see what our limiting reactant is, if there is one. So I'm going to write this down, number down on a piece of paper. That way I can erase what's shown so far. And we can keep using it. So, okay. So I'll have to rewrite. Hey, that worked out. It actually kept that part for me. Did it? Okay. I don't know why it only erased that one part, but that's what I wanted it to do. That's awesome. So, now we're going to convert our 0.0375 moles of NaCl. We're going to convert it to AgCl. And this is just a 1-to-1 relationship. 1 mole of NaCl, 1 mole of AgCl. So we would get that we would form 0.0375 moles of silver chloride solid. We're then going to do the same thing here where we have 0.0375 moles of our silver nitrate. We're going to convert it via a 1-to-1 relationship. 1 mole of silver nitrate makes 1 mole of silver chloride. And from that, we would also get 0.0375 moles of our silver chloride solid. So one thing to note in this problem is since they're both exactly the same, that means we don't really have a limiting reactant. Either can be limiting. So you can use either number you want. Clearly it wouldn't change it. We're going to get 0.0375 moles either way. So there's only one last step. The problem asks us what would the mass of the solid be. 0.0375 moles of silver chloride. We're going to convert that. And we're going to get that for every 1 mole of silver chloride, it's going to have a mass of, I'm going to look this up, silver 107.87, and then chlorine 35.45. So every mole of that is going to have a mass of 143.32 grams. So therefore we multiply those together, and we get that we're going to form a total of 5.37 grams, you'll notice 3 sig figs, because that's how many are in the problem, of silver chloride. You'll notice something else. The problem told us that we made the solution a total volume of 1.5 liters, and we diluted it to that. Why didn't I use that? The reason for that is there's nowhere in the problem where it asks me about the final solution. I have a mass of a solid at the end. That doesn't change that. And the source of the moles all come from the initial addition of 15 milliliters of 2.5 molar silver chloride and 25 milliliters of silver nitrate. Nowhere do I add more moles of either of those, so I don't need to use that volume anywhere else. If it had asked me for the concentration of either the sodium or the nitrate ion, I could have used that new volume as the new solution volume. But since it didn't ask me for that, that ended up just being extra information because Nowhere do I actually use the diluted solution to do anything, because the mass of the solid doesn't depend on the volume of my solution, but instead only on the initial volumes where we actually get the compounds from. Okay, and this last slide we had was just a big long explanation of why I did that and how you would deal with that. That was nothing extra. There's no extra problems in that slide. So I know there was a bunch of these, but hopefully it helped out, especially because now we've got some that look a lot like Chapter 8. A few of these were really Chapter 8 questions, and then a bunch of Chapter 9 questions where you have to work on identifying which problem you do where.